All right, let's get into it. We're going to talk about one of the most maddening parts of modern life, the traffic jam. But the solution I'm about to show you, it isn't about building more roads or bigger bridges. No, it's something way, way bigger. You know that feeling, right? That slow, agonizing creep forward, staring into a sea of red taillights, and you're just convinced you picked the slowest lane. It's a headache we all share. And this is pretty much how researchers see it too. They use this amazing tool called SUMO, which stands for Simulation of Urban Mobility, to create these digital versions of our cities. And just look at it. Even in the simulation, these digital cars are stuck in the exact same gridlock as us. So let's just take a second to talk about the real impact of this problem. I mean, what is this daily gridlock really costing us? And you'll see, it's a whole lot more than just a few minutes of our day. I mean, it's a massive drain, right? It wastes our time, burns through fuel, which costs us money and pollutes the air. And let's be real, it's a huge source of stress. So finding a fix for this, it isn't just about convenience. It's about a major improvement to our quality of life. But okay, if the problem is so obvious, why is it so darn hard to solve? Well, the answer isn't really about engineering or building new things. It's all about the mind-boggling math hiding just beneath the surface. I mean, it seems like a pretty simple question, doesn't it? Why don't we just program the lights to be smarter? Find the perfect timing to keep everything moving. How hard could that possibly be? Well, let's look at the numbers for what seems like a small network. Just 13 traffic lights. This is how hard it is. That's 90 to the power of 13. We're talking about a number so huge, it doesn't even have a common name. So here's the deal. If each of those 13 traffic lights can stay green for anywhere between 10 and 100 seconds, that's 90 different options for each light. The total number of combinations is, well, it's in the thousands of trillions. If you had a computer test every single one, even one per minute, it would still be running for thousands of years. So yeah, brute force is just not an option. Okay, so if we can't just brute force it, how in the world do we find the right answer buried in trillions of wrong ones? Well, this is where we get creative. We start looking for inspiration from the greatest problem solver there is, nature itself. Scientists use something called heuristic methods. Now, that's just a fancy way of saying they use smart shortcuts. Instead of checking every single possibility, these algorithms use strategies that are inspired by billions of years of evolution to find really good or even near-perfect solutions in just a tiny fraction of the time. And here are two really cool examples. On the left, you've got the genetic algorithm. It basically mimics evolution. You start with a bunch of random traffic timings, test them out, and then only the best ones get to survive and breed to create the next generation. It's survival of the fittest for traffic lights. Then on the right, there's particle swarm, which is inspired by a flock of birds. Each particle is a possible solution, and they all fly around together, telling each other where they've found the best stuff, or in our case, the best traffic flow. Now, these methods are really powerful, for sure. But researchers found an even better model out there in nature. I mean, what if you designed your algorithm not on birds, but on a much, much bigger, more strategic hunter? And that brings us to the Whale Optimization Algorithm, or WOA for short. It's a newer, super powerful method that models its entire strategy on the unique and really clever way that humpback whales hunt their food. It is absolutely fascinating stuff. So how does it actually work? Well, first, the algorithm creates a pod of random solutions. Then it figures out which one is the best so far, and that becomes the prey. From there, all the other solutions, our digital whales, start to encircle that prey. They use this really unique spiral motion, just like real whales making a bubble net, to close in on it. And this is the brilliant part. The whales are focused on the best target they've found, but that spiral motion lets them explore the area right around it for an even better option. This keeps the algorithm from getting stuck on a solution that's just good when a perfect one might be right next door. Okay, so we've got our contenders, right? The evolution-based algorithm, the flock of birds, and the pod of hunting whales. Researchers put them all to the test on a really complex city network to see, once and for all, which strategy was the best. And the results? Well, they're pretty clear. This table shows the average travel time each algorithm managed to achieve. The BAT algorithm, which is another one inspired by nature, gets it to 318 seconds. The genetic algorithm does better, 270. Our flock of birds, the particle swarm, gets it down to 210. But just look at that bottom row. The whale optimization algorithm, it crushes it, bringing the average travel time down to just 175 seconds. I mean, that is a huge improvement. So the takeaway here is pretty simple. When the problem gets really big and really messy, that clever hunting strategy of the whale turns out to be the most effective way to cut through all the complexity and find the best path. Okay, this is all super interesting research, but what does it actually mean for you and me, for our daily commute? This is where it gets really exciting. Because here, researchers compared the wheel algorithm to the methods traffic engineers are actually using today to program our traffic lights. Things like the Webster method and even the best commercial software out there. And just look at these numbers. The best software gets travel time down to 92 seconds. The wheel algorithm, it cuts that almost in half, down to less than 56 seconds.
Let's just put a spotlight on that improvement. 39%. That is a massive leap forward.
Just think about what that really means. It's not just about saving a few seconds here and there. We're talking about the potential to cut almost 40% off the time you spend just stuck at red lights. That means less time in the car, less fuel burned, and a way smoother, less stressful commute for all of us. And that's really the thought I want to leave you with. By copying these elegant solutions that nature has already perfected, we're on the verge of solving a problem that's been making our cities miserable for decades. It just makes you wonder, right? What other huge human-made problems are just waiting for a solution that's been swimming in our oceans or flying in our skies this whole time?